Hey there, fellow knowledge seekers. Are you ready to dive deep into a topic that's truly electrifying?
You bet. We're going to untangle all those wires and make electricity crystal clear.
You've sent us some really interesting research and notes on electricity, so let's jump right in. What is electric current? I mean, we can't see it, but it's what makes our world go round.
It really is fascinating. Think of it like a flow. Just like water flowing in a river, an electric current is a flow of electric charges.
Okay, so what's actually flowing?
Tiny particles called electrons. They're moving through a conductor, like a wire, carrying their electric charge with them.
It's like an invisible river of electrons.
Exactly. And just like a river needs a channel, that flow of electrons needs a path. A closed loop we call a circuit.
Ah, okay. So the electric current flows from a source, like a battery, through the circuit and then back to the source.
That's the idea. It's a continuous loop. But there's a bit of a historical quirk about the direction of electric current.
Oh, tell me about it. It always seemed a bit backwards to me.
Well, back in the day, before scientists knew about electrons, they thought positive charges were moving. So they defined the direction of current from positive to negative.
Even though it's the electrons, the negative charges, that are actually doing the moving.
You got it. But for practical purposes, it doesn't really change how circuits work. The important thing is we all agree on how to talk about it.
Got it. So we've got these electrons flowing through a circuit. How do we measure how much electricity is flowing?
We use a device called an ammeter, and the unit of measurement is the ampere. We often just say amps or use the letter A.
What about when we're talking about really tiny currents, like in those super small electronics?
Then we use smaller units, just like we use millimeters or micrometers for tiny distances.
Okay, so what are the units for those tiny currents?
There's the milliampere, which is 1,000th of an amp. It's written as MA.
And even smaller.
The microampere, that's 1 millionth of an amp. It's written as A.
Okay, so like a tiny circuit using 5 humans, a really small amount of electricity.
Exactly. Those small units help us be precise when we're dealing with those tiny currents.
So we've talked about electric current, this flow of electrons, but what's the force that gets them moving in the first place? What makes them flow through the circuit?
That's a great question. It all comes down to electric potential, or what we often call voltage.
Voltage. Okay, so help me understand this. How does it relate to the flow of electrons?
Think about it like water flowing downhill. The higher the hill, the more potential energy the water has, and the faster it will flow.
So in an electrical circuit, it's like there's an electrical hill.
Exactly. And that hill is what we call the potential difference, or voltage. It's what pushes the electrons along.
So what creates this potential difference?
A source, like a battery. It acts like a pump, maintaining a difference in electrical potential energy between its two terminals.
So a battery is like a pump, and the voltage is a measure of how strong that pump is.
You got it. Voltage is measured in volts, and it tells us how much push is behind those electrons.
So a higher voltage means a stronger push, and that means more current will flow.
Right. Precisely. That's the basic idea. A higher voltage will create a stronger force, pushing those electrons through the circuit with more oomph.
I'm starting to see how all these pieces fit together. But before we go any further, let's pause for a second and make sure we've really got a handle on this idea of electric potential.
Absolutely. Electric potential, which we usually call voltage, is all about potential energy per unit of charge. It's the force behind the flow of charges.
Okay, that makes sense. So more voltage equals a stronger push, and that leads to more current. And it's all thanks to sources like batteries that maintain that potential difference.
You got it. You're really starting to get the hang of this.
Now, I'm really curious about how voltage and current are related. I'm guessing it's not quite as simple as higher voltage, higher current, is it?
You're right. There's another key player here that we need to talk about. Resistance.
Resistance. Okay, I'm intrigued. Let's dive into that next.
Welcome back. Ready to keep exploring?
You bet. I'm ready to tackle this thing called resistance.
All right. Resistance is a bit like a gatekeeper in an electrical circuit.
A gatekeeper. Okay, I'm listening.
Imagine a highway. A wide, smooth highway lets cars flow freely. But a narrow, bumpy road slows them down.
Ah, I see where you're going with this. So is resistance like the bumps in the electrical highway?
Exactly. It's a measure of how much a material resists the flow of those electrons, those tiny charges we talked about.
So more resistance means it's harder for the electrons to flow.
That's it. And that's actually important because that resistance is what turns electrical energy into other forms of energy, like heat or light.
Oh, interesting. So that's why my phone gets warm when I'm using it a lot.
Exactly. The resistance in the components is converting some of that electrical energy into heat.
So resistance isn't necessarily a bad thing.
Not at all. It's what makes so many electrical devices possible. Think about it. Without resistance, we wouldn't have things like toasters or light bulbs.
That's a good point. Okay, so how do we measure resistance?
We use a unit called the ohm, and it's represented by the Greek letter omega, which looks like this, AA. The higher the resistance, the more a material opposes that flow of current.
Makes sense. But why do some materials have higher resistance than others? What makes something a good conductor or a bad conductor?
It all boils down to their atomic structure. Some materials have electrons that are loosely bound to their atoms.
So they can easily jump from atom to atom.
Exactly. That's what makes them good conductors, like copper or aluminum. But in other materials, the electrons are held more tightly.
So they can't move as freely.
Right, those are insulators, like rubber or glass. It's like the difference between a smooth highway and a bumpy road for those electrons.
I like that analogy. So a thicker wire would be like a wider highway, lower resistance.
Exactly. You're getting it.
Right.
A thicker wire gives those electrons more space to move around, so there's less resistance.
Okay, I think I'm starting to wrap my head around this resistance thing. Now, I'm really curious about how it all ties together with voltage and current.
That's a perfect segue. There's a fundamental relationship between those three things, and it's called Ohm's law.
Ohm's law. I've heard of it, but I'll be honest, it always sounded a bit intimidating.
It's really not that complicated. It basically says that the current flowing through a conductor is directly proportional to the voltage across it and inversely proportional to the resistance.
Okay, break that down for me.
More voltage means more current, but more resistance means less current.
So it's like a balancing act between those three factors.
You got it. And there's a simple formula that captures this relationship. Current I equals voltage V divided by resistance R.
So if I know two of those values, I can calculate the third one.
Exactly. It's a really handy tool for understanding and working with circuits.
This is starting to click. Ohm's law is like the key to understanding how those three factors work together.
It really is. It helps us make sense of how voltage pushes the current and how resistance tries to hold it back.
Okay, before we move on, could you quickly recap the key points about resistance?
Sure thing. Resistance is the opposition to current flow, and it's measured in ohms. Different materials have different resistances depending on their atomic structure. Good conductors have low resistance, and insulators have high resistance. And we can't forget about Ohm's law. Current equals voltage divided by resistance.
Okay, got it. That's a great summary. Now, I'm curious about how resistors are actually used in circuits.
Oh, resistors are incredibly versatile. We use them for all sorts of things.
Like what? Give me some examples.
Well, one common use is to limit the current in a circuit. Like, you know how we talked about your phone getting warm? We use resistors to make sure the current flowing through delicate components doesn't get too high and damage them.
So it's kind of like a safety valve.
Exactly. We can also use resistors to divide voltage, create timing circuits, and tons of other things.
They sound pretty important.
They are, and they get even more crucial when we start talking about microelectronics and all those tiny complex circuits.
So we've got these resistors, and we're putting them into circuits. What happens when we combine multiple resistors?
That's where things get even more interesting. It all depends on how we connect them, either in series or in parallel.
Okay, I'm ready to hear about series and parallel connections.
Ah!
All right, let's dive into these series and parallel connections. It sounds like that's where the real magic happens in circuits.
You got it. This is where we start building real-world circuits.
So let's start with series connections. What's going on when resistors are connected one after the other, like links in a chain?
In a series connection, think of it like a single-lane road. The same traffic has to flow through each point on that road.
So every electron has to go through every resistor in the circuit.
That's the idea. There's only one path for those electrons to follow, and that means the total resistance in a series circuit is just the sum of all the individual resistances.
Okay, so if I have three resistors, say 2 ohms, 3 ohms, and 5 ohms, the total resistance is 10 ohms.
Exactly. It's as simple as adding them up. And since the current is the same throughout a series circuit, we can use Ohm's law to figure out how much voltage drops across each resistor.
Makes sense. Now, what about parallel connections? Those are the ones where the resistors are side by side, right?
Right. Think of this one like a highway with multiple lanes. Cars can choose different paths to get to their destination.
Ah, so the electrons can split up and take different routes through the resistors.
You got it. And that's where things get a little counterintuitive. In a parallel circuit, the total resistance is actually lower than the resistance of any individual resistor.
Wait, really? Adding more resistors makes the total resistance go down.
It does. It seems strange, but it's because you're giving the current more paths to flow through. It's like adding more lanes to that highway. It reduces the overall congestion.
Okay, that's pretty cool. So adding more branches in parallel actually makes it easier for the current to flow.
Exactly. You're getting it.
This is really helping me understand how circuits work. Could you do a quick recap of the key differences between series and parallel, just to make sure I've got it straight?
Sure. In a series circuit, the current is the same everywhere. The total resistance is just the sum of the individual resistances. In a parallel circuit, the current splits up, and the total resistance is actually less than any of the individual resistors.
Got it. So series is like a single-lane road, and parallel is like a multi-lane highway.
Perfect analogy.
Now, I'm curious about where we actually see these series and parallel connections in the real world.
Oh, they're everywhere. Think about the wiring in your house. All those outlets you plug things into those are connected in parallel.
So I can have my lamp, computer, and phone charger all plugged in and working at the same time.
Exactly. They each have their own path to the power source, and they all get the same voltage.
And that's why if one thing stops working, the others are fine.
You got it. Each appliance is on its own separate branch. Now think about Christmas lights. Have you ever noticed that if one bulb burns out, the whole string goes dark?
Yeah. It's always a pain trying to figure out which bulb is the bad one.
Well, that's because a lot of those strings are wired in series. If one bulb breaks the circuit, the whole thing stops working.
Makes sense. So series circuits are used when we need to control the current very precisely. And parallel circuits are used when we need to power multiple things independently.
Exactly. You've got it. Series and parallel connections are the building blocks of almost every electrical circuit you can imagine.
Wow, we've covered a lot of ground today. From tiny electrons flowing through wires to the way resistors shape the flow of current in circuits.
It's been a great journey. And it all comes back to those fundamental concepts: current, voltage, and resistance.
Ohm's law, series and parallel connections. It's all starting to make sense. I hope our listeners feel like they've had a real aha moment with electricity today.
Me too. It's amazing how much we rely on electricity in our modern world.
Absolutely. And it's all thanks to those tiny electrons zipping around, doing their thing.
To all our listeners out there, keep those questions coming. We'll be back to tackle another electrifying topic soon.
Until then, stay curious.